you could go to the agenda slide. Perfect. I think we're good, folks. Thanks for bearing with us. Okay, so today's session is going to be focused on artificial intelligence and machine learning. And in particular, this is really critical in the way that customers are consuming cybersecurity technologies and the way they're identifying new and evolving threats. And so what we're going to do today is to walk you through a number of different topics as it relates to AI and machine learning. Specifically, we're going to have our guest presenter really define what those concepts are and talk about the differences between the two so that you have a good understanding as to what those terms mean. We're going to talk about machine learning in particular and data analytics as it relates to how we use it to provide threat detection in the cybersecurity world. And then we're going to talk about the impact of the cloud and the impact that it has on your business. So pretty full, robust agenda. With that, Jeet, if you can go to the next slide. So let me introduce our guest speaker for today, Dr. Jeet Duda. Jeet is our Director of Data Science here at Adlumin. He's got a lot of experience with data analytics and applying data analytics to optimizing performance and making business decisions, and in particular using those skills and transferring them over to the cybersecurity world. Jeet, let me ask you if you could just maybe even give a little bit of your background. You have a fascinating background. You've done some interesting things. Could you just describe your background a little bit, and then I'll just turn it over to you for the balance of the presentation.
Sure. Thanks, Jim. Hi, everyone. My name is Jeet. And yeah, my background is in economics. I started out as a practicing economist. I did, for the most part, macroeconomic forecasting. So I built econometric models that predict outcomes in the economy for different audiences. I did that for quite a while, and then I had an opportunity to go into the world of data science, which is an expansion of the techniques and just the amount of data that's available to you than is typically the case in most macroeconomic forecasting situations. And in my capacity as a data scientist, I worked on some very interesting projects for a large bank where we built forecasting models for outcomes based on bank policies and different incentives the bank provided, and what were the impacts of those policies on whether or not we were able to win more customers or customer satisfaction. So data science applications in improving customer experience or in improving the profitability of any given product idea is what I primarily worked on. And then in my current role at Adlumin, I lead our data science team, and where we are building applications that allow cybersecurity teams to better manage just the sheer volume of data is immense, and the data science applications that we are building help our clients manage that volume of data and gain quicker and sharper insights from that data.
Outstanding. Sounds like you got an amazing background, and we're really interested to learn from you. So with that, Jeet, take it away.
Thanks, Jim. So artificial intelligence and machine learning, the terms are often used interchangeably, but to be accurate, artificial intelligence is actually the broader concept of the two. AI is the computer counterpart of human intelligence, and machine learning is how you build artificially intelligent systems. So the idea is to give machines the ability to make decisions in a similar way that humans do. So think of complex or complicated decisions that get made via a series of simple yes/no decisions, or humans learning via feedback loops, how we tend to learn from our mistakes. And so the idea is to take a similar approach to teach a machine how to make decisions. And if you teach it well, then the machine learns, hence the terminology, machine learning. So to put it in a nutshell, machine learning is a set of techniques or a large family of mathematical techniques and methods that allow computers to learn from data, and that's how you build artificially intelligent systems. So for example, when you play chess against the computer, that's an AI system. Or you could have a stock trading AI that can automatically make buy, sell decisions, for example. And in our case, and for at Adlumin, we have an AI system that can find suspicious logins, for example, from billions of such events without human intervention. And that's just one example from several AI machine learning use cases that we have deployed on the Adlumin platform. And the way a data scientist will operationalize this idea, the idea of letting machines learn, is by writing an algorithm, which is a series of rules for how the computer will interact with the data. These algorithms, they have certain requirements. They must be able to handle vast amounts of data and learn from that data how to make quote unquote good choices. And how you define good is the algorithm itself tells the computer what outcomes are good. So to go back to one of our examples, when you're buying a stock, if you buy a stock and then it subsequently goes up in price, that's an example of a good outcome. And we can write that into the algorithm. And over time, with enough data and well written, and if your algorithm is well written, then the machine might learn to always buy good stocks. So the way we facilitate a machine for learning is to build these feedback loops in the algorithm. When the machine gets it right, you have a loss function in the algorithm that essentially drops to zero because there's no gap between the decision that the machine made and the correct decision. But when the actual correct value and what the machine came up with are different, then the loss function, it accumulates a penalty. So it's sort of like a carrot and stick approach. The machine gets to optimize this loss function for long enough with plenty of data, it eventually learns to make correct decisions most of the time. So in the next slide, let's talk a little bit more about some specific, what the specific use cases are for machine learning to be practiced in the cybersecurity domain. So first of all, what's the urgency of using machine learning in cybersecurity? So you can have a well-configured, well-managed network with good policies, procedures, and checks in place, but attacks will still happen, and really insidious attacks with bad consequences. Your data could be stolen, and the day-to-day operations of an organization could be disrupted. And we have had quite a few high-profile incidents just in the last couple of years, right? So a key realization here then is that security rules are not enough to safeguard networks. A firewall generates thousands of alerts a day, so that's just not feasible for security professionals to chase down. So what you need then is a data science layer to boost the signal to noise ratio. And that's what makes the task a lot more manageable. And once an algorithm has sifted through the data, then you create a much more of a target-rich environment for security analysts to perform follow-up analysis. And also, there are these network intrusion prevention or detection systems that you can install. but many of them will have machine learning applications in them, especially the ones that aim to protect against zero-day attacks. These are attacks that have no known signatures or examples, so they require anomaly detection in the network traffic, and that's how you can either prevent them or detect them after the fact. And that is best done via a machine learning algorithm. And but again, even with such systems in place, attackers can still gain footholds inside the network, and thereafter they can conduct malicious activity. And to defend, to detect such attacks, you again need an AI-based recognition when something unusual is going on. And this is very likely going to be at the host level or at the user level. One other thing I'll mention is that machine learning can play a critical role uh, after the attack. So post breach, you need a way to systematically track down emails or other forms of interaction with the attacker once that attacker entity is identified. And if you are able to track all of your communication with that attacker, it will help you assess the damage a lot more accurately. So even if you miss the attack in real time, if you have good retention of your data, then machine learning models can help with that assessment. And that's often a necessary first step in preventing such attacks in the future.
So gee, so thanks for underscoring the importance of a machine learning layer in any cybersecurity operation. Can you talk about some of the challenges that are specific to this domain? What does a machine learning practitioner need to look out for when applying these techniques in cybersecurity?
Sure, Jim. So let's go over some of the challenges in implementing this. So it's and that's going to be my next slide. So what's important to realize is that these threats are constantly evolving, and most types of threats don't have a signature pattern, so to speak. Like there is not a set of actions or a sequence of events that you can point to and say, wow, right there, that's signaling a malicious attack. So your algorithm needs to be flexible in design and not rules based. For example, you could say that if an individual user logs on to a machine they normally don't, or you could say that that's a red flag. So you could write an alert on these so-called novel logins. But the problem is that there are other entities, like network administrators often need to access machines that they previously have not or normally don't. And so this rules-based algorithm will throw up a lot of false positive alerts. The challenge then is to define what's abnormal in a deeper kind of way. And one way to do this is that you take that novel login rule as just as a starting point, but you build in a lot of other measurement as in order to make that determination what's abnormal. Like you need to add to your threat detection criteria. For example, you could study the daily login behavior of each user and construct a baseline, um, and store in that baseline information like what kind of behavior does this user engage in, how many logins, to which systems and servers, for example. And what you end up with then is a much fuller picture of activity for each user. And then you might be more accurate in flagging truly suspicious behavior. And one other point I'll make is that machine learning detections will rely on a probability calculation and thresholding. So like you're rolling dice, what's the probability of a pair of sixes? That kind of way. So and so that means that the algorithm will return a probability score that you can compare against a threshold value, and you can then set that, you can tune that, and that gives you more control over how sensitive you want this detection to be. So if you set the threshold really high, then the bar is really high. Something has to be super unusual for your system to detect. And when you set this threshold to some kind of sweet spot where you get a good number of alerts but are not overwhelmed with false positives is the idea. So that's another advantage that machine learning has over something that is purely rules-based threat detection. So that is a challenge that is definitely worth overcoming. And one other idea I'll mention next, and it kind of falls into the set of challenges that machine learning practitioners face in the cybersecurity domain, is that, so keep in mind that you need two things to train a machine to learn. You need good data, and you need an algorithm for teaching the machine how to tell good outcomes from bad. And the challenge here is that we have a lack of labeled data sets, what we call in machine learning labeled data sets. So for example, at Adlumin, we see abnormal things in our in data from various clients, but there's not a lot of confirmed instances of malicious activity. So not a lot of historical databases of known malicious attacks in our case. And this is what is called labeling in machine learning. To illustrate the challenge with an example, if you are trying to, let's say, detect credit card fraud, and again, this is just a contrasting example. In credit card fraud detection, you have a much better chance of getting hold of a data set that has instances of fraud clearly labeled as such. And then you can train an algorithm to learn from those instances what were the signals from those cases that we can apply to prevent future fraud is the idea. But in network security, we don't have such labeled data sets. So we have to rely mostly on what's called unsupervised machine learning techniques. And unsupervised models are where you're not trying to predict a specific fraud versus no fraud label, but you're trying to separate the data in clusters maybe, and then flagging data points that kind of stand isolated from the cluster where everyone else is. Or you could be drawing connected networks of user behavior, or what machines and hosts a user connects to on a daily basis. You can have a graphical representation of that activity, and then you're trying to find shapes that look funny. So this approach is fine. You probably get to algorithms that are less wedded to the historical data, and you can better classify new data points. But it is challenging nonetheless to test these types of unsupervised models. You kind of have to play it by ear a bit. And finally, one other challenge I'll mention is that most of data science is about converting things that are not numbers into numbers. And then you can analyze them using mathematical techniques, like words and pictures are given a numerical representation. And this type of numerical representation is harder to achieve in cybersecurity data, which can limit the type of machine learning approaches we can try in our work. But this is a very interesting challenge to solve, and we are very actively working on this at Adlumin.
So that's great. Very interesting. Let's talk a little bit about cloud. So we here at Adlumin, we pride ourselves of being cloud native. The entire platform is conceived and engineered in the cloud. How big a deal is it, the cloud, when it comes to applying machine learning models?
Great point, Jim. The cloud is just absolutely vital for creating the infrastructure for hosting these machine learning based detection systems that I've been talking about. Adlumin can process billions of data points a day and provide these security layers at a reasonable cost, thanks to the power of cloud computing. The key problem we are solving here is applying machine learning detections on streaming data. So billions of network security event logs and system logs from users, and these logs are streaming nonstop, right? So our model training and detection has to happen in parallel without interrupting the flow of data. And our solutions to these challenges are based on cloud computing building blocks. So all the necessary steps like ingesting the data, storing the data, and model application, these stages have cloud-based solutions in our platform. We have built a serverless architecture that scales instantly with demand, and this gives us virtually endless processing power. As much processing power is needed at any given moment based on demand. And we have built data lakes in the cloud that allow vast amount of storage. So, and that too allows us to build an effective data science layer, including the post-breach analytics that I mentioned earlier. That is so crucial for assessing damage and determining what follow-up action a security analyst needs to take. So really we couldn't do this without the cloud. Jim, are you on mute?
Yeah, yeah. So sorry about that. Gee, just kind of a random question here, but what are the key takeaways? What are the things that you really would people should be thinking about as they are thinking about their cybersecurity posture and how they better protect themselves? What are the key takeaways that you want them to remember and walk away with and say, this is important that you should be thinking about with your next SIM or security solution?
Sure. So key takeaway number one in my mind is just how necessary a machine learning data science layer is in managing the security related information, just the flood barrage of information that's coming your way every day. And with the help of a well-written machine learning algorithm, the task becomes so much more manageable. Let the machine do a lot of the heavy lifting in terms of finding something unusual, finding that needle in the haystack, and maybe a few needles, and then you're able to kind of examine them in more detail, rely on your security team that has more domain knowledge to then chase those more promising or more likely instances of malicious activity. And another takeaway is just to be mindful of the data requirements and challenges in building machine learning algorithms. There is a lot of processing of the raw data that you're going to ingest that needs to happen before any kind of machine learning algorithm can be trained. The data has to be, a lot of the data we get in cybersecurity is not going to be numerical. And even with categorical data, the number of categories is just going to be so large that you're going to need some specialized techniques and some creativity in order to transform that data that doesn't look like something that machine learning can be applied to something that yes is amenable to machine learning. So doing those transformations, building that skill set is critical. And then the final point, again, I'll go back to having just the benefits, the technology, the set of technology options that open up when you are doing this all in the cloud. Just those pieces that are necessary to pipeline the data just the right way. And without interrupting the flow of data that you're receiving, training a model, and then applying that model on new incoming data to flag instances of suspicious activity. The role that the cloud plays, the technology choices that it affords, you need either the cloud itself or something comparable.
Great. Gee, thank you very much. We appreciate your walking us through this. If you don't mind, if you could stick around for just a moment, just to see if there's any questions at the end. And folks, again, we'll open it up at the end if you have any questions. Again, put them in the chat window or their question panel. So, folks, for all of our customers that are on the call today, what's next? Again, Adlumin was built as a cloud-native serverless architecture built on AI and machine learning. But we have a lot of information and documentation on our website, not only on the platform and the business and technology benefits of what Adlumin does, but also on machine learning and some of the points that Jeet mentioned. So feel free to go there and take a look at that, as well as our ongoing blog posts that describe in additional detail some of the things that Jeet covered. Also, we would offer you, if you have an interest in seeing some of these principles at play here, feel free to reach out to us. We'll be distributing, again, a replay of this session, but feel free to reach out to us and schedule a private tour of the platform where we'll walk you through the various components of the Adlumin platform and how they operate and how machine learning's been implemented to be able to solve cybersecurity problems. Additionally, we also provide a free, no obligation, 2-week proof of value for your organization. So if you want to see how Adlumin can actually operate in your own environment, looking at your own data and adjusting the devices within your infrastructure, it's a great way to see the impact and actually what's happening in your network. So those are some of the next steps. With that, Jeet, if we could just go to the next slide, if you would. And I think we'll open it up to any questions. Again, if you have any questions, folks, raise your hand using the hand icon in GoToMeeting, and or put a question in your chat or a question window. I do see a question here. Jeet, I'm going to read it. How is machine learning different from traditional statistical methods? How's machine learning different from statistical methods?
Good question. I see that question a lot, and I have grappled with that question myself quite a bit. Like I mentioned, my background was not in machine or what is considered to be today to be data, strictly speaking, data science. I was more of a traditional quant. So I've had familiarity with many of those traditional, quote unquote, traditional statistical methods for quite some time. So what's the difference between that and machine learning, traditional statistics versus machine learning? The way I've come to understand it is that really all of those traditional statistical methods are folded into within the large grand family of methods that constitute machine learning. So let's say you're going to do a distribution, you're going to compare two distributions, you're going to estimate, or if you have a sample of data and you want to estimate the distribution that it came from, you could do parametric or non-parametric methods for estimating that unknown density. This is an age-old traditional statistical method, right? But it is routinely used in many of the machine learning applications that we build today. So all of traditional statistics is part of the machine learning toolkit. And then there have been innovations in recent decades and even in recent years that thanks to the widespread availability of data and computing power, there are some other techniques that have now become feasible. Like you could build, if building a single decision tree is a traditional statistical method, then building an ensemble of trees, training many trees at once in some kind of random sampling kind of way, let's say a random forest, is more of a what you might call machine learning data science. So those innovations have happened as a result of more computing capacity being available to us, and for our algorithms to be exposed to more data. But all of the traditional toolkit of statistics are still fair game.
Okay, okay, thank you. Let me check another chat. Do you rank, order, or prioritize the threats that your algorithms detect?
Yes, yes, that's a good question. We do something I mentioned during my presentation was that one benefit of using a machine learning algorithm to detect threats as opposed to something that's rules based only is that a machine learning algorithm will, in almost all cases, return a probability, right? Like how likely is this particular event, how likely is it to be a malicious one? And so when you get that probability score, that allows you to rank order the detections you're raising in like as on some scale of severity. So all the detections that we raise have a security label that gets attached to them based on that probability score. So something that has like a mildly probable suspicious event, we would typically grade it as informational, for example, when we send that detection out on the severity scale. And then informational, something could be of medium severity, high severity, critical severity, and so on. So we do rank order all of our detections, and thanks to just the inherent nature of how machine learning surfaces detections, it is quite easy and sensible to do.
Okay, okay, thank you. Let me check. I do not see any more questions or chats at this point, so I think we're good. If you could just go to the next slide, Jeet. So again, here's our contact information. If you have any questions specific to this session that we just covered today, or in general about Adlumin, feel free to reach out to us. Again, we're going to be distributing a replay of this for you to play later on and or distribute your organization as is appropriate. Look out for our next session that we're going to be doing in May. And again, we hope that these sessions are valuable to you to provide information and education about some of the key topics that are happening in cybersecurity and how you can use them to better equip your security posture to protect your organization. So with that, again, I want to thank you for taking time out of your day and for joining us on the session today. Jeet, I want to thank you for your insight and your expertise on this topic and being our presenter. And folks, that's it. We look forward to speaking to you in May. And please feel free to reach out if you need anything from us. With that, have a great day. Bye-bye.